So up until this point, we've done very simple derivatives, right? I mean, move the exponent in front, subtract 1, a few quirky exponents, but other than that, nothing too difficult, right? So you start getting to more difficult type equations, and while a lot of these you could still solve via your original way of solving, there are some shortcuts. And then we're going to get into chain rule that you really need to use these to do the chain rule, or you're going to be foiling, forever and having to do a huge type of workaround. And so the first one is the product rule. The product rule is what happens when you have two different functions that are being multiplied together. And when you have these two functions being multiplied together, you, instead of actually multiplying the functions out, you can take the derivative of each and put them together. And so the rule is that you take, and I actually write this differently, and I'll explain why. If you write this the way that I tell you to write it, then it's going to be just like the quotient rule. They switch it for some reason in the book. So I always say, when I do the product rule, the derivative of the first times the second plus the first derivative of the second. All right. Because this is addition, so it really actually doesn't matter what order you do it in, but the quotient rule is subtraction, and that's the order it's in for the quotient rule. And so if you memorize this order for the product rule, then it's the same order for the quotient rule. It's just subtraction. So derivative of the first times the second plus the first derivative of the second. All right? Yes. So this is the first example. I would label this the first one and the second one. And so typically when you do this, it might be a good idea to go ahead and figure out what the derivative of the first one is. That's going to be 3 minus 4x. And the derivative of the second one then is just going to be 4. And so now that I know that, I can just plug it into my product rule. So then the derivative of this guy is going to be the derivative of the first. Well, that's 3 minus 4x. Times the original second, that's 5 plus 4x, all right? And then plus the first, the original first, which is 3x minus 2x squared, times the derivative of the second, which is 4. And then you do want to simplify this. You don't want to leave it like this. That's ugly. So you do want to simplify it using your foiling and all. So we're going to distribute our 3. We have 15 plus 12x. Distribute your negative 4x. We have negative 20x minus 16x squared. Distribute your 4, 12x minus 8x squared. And then combine your like terms, highest to lowest, because this is should be standard form. Yeah, so we're going to do this guy and this guy. And then we have positive 12, negative 20, positive 12. So that's going to give us a 4. And then we have 15. And so the derivative of this is going to be negative 24x squared plus 4x plus 15. All right, so product rule using trig. So first of all, you have to recall the two trig functions we've talked about so far. The derivative of sine is cosine, derivative of cosine is negative sine, right? And other than that, you're going to do this exactly the same. For this one, this would be my f of x, this would be my g of x. So then my derivative of my f would just be 1, and my derivative of my g would be cosine. And then I'm going to just plug that in. So I'm going to say the derivative of the first times the second plus the first derivative of the second. And so I basically just, and I can't simplify that anymore, right? So I have sine x plus x cosine x, and that is my first derivative here. So look at this one, example 3. Example 3 actually uses multi-parts here. The first one you're going to use the product rule for, the second one you're not, because the second one just has a coefficient. You don't need to use the product rule for 2 sine x. There's technically not 2 functions there, right? So for the first part of this, you have f of x, g of x, but this is just one function. And so I'm going to use the product rule for this first part. My derivative of this guy is just 2. My derivative of this guy is negative sine of x. So I'm going to say derivative of the first times the second plus the first derivative of the second minus, and then I have to do the derivative of this. Well, that's just going to be 2 times the derivative of sine, which is just cosine. So I have 2 cosine x minus 2 cosine x. Those cancel. And then I have 2x times negative sine x. So I'm just going to pull that negative out in front. 2x sine x. That is my derivative here. So product rule, you can see, you could FOIL at the beginning for some of these, unless we get into the chain rule, but, and then possibly do just a standard derivative. Quotient rule is a little more difficult because you'd have to actually divide, like long division divide, and get it, which most people would not opt to do. So for this one, and I actually write it the same way. I do the derivative of the first, which is technically the top. So the derivative of the top times the bottom minus the top derivative of the bottom all over the bottom squared. And this is the original bottom, not the derivative of the bottom. All right. So I write it in the same order. It's just subtraction. And then you also divide by the square of the bottom. Now this, keep in mind, is considering the fact that the domain is restricted by when the denominator is 0. So it is a restricted domain because you are doing division for these. So look at the first example, example 4 here. So my top function is 5x minus 2. So my derivative of the top here is just 5. My bottom is x squared plus 1, so my derivative here is 2x. And then I'm just going to plug it in. The derivative of the top times the bottom. Minus, this one is subtraction. We have the bottom derivative of the top. And that's all over the bottom function squared. You're going to distribute the number one. What do you think my number one error here is when I see people do this? Number one error. That negative, distribute the negative, yeah. And you can't cancel. Yes, some people do try to cancel, and you cannot cancel. So some people will try to do this. You can't because it's partial. And then, yes, distributing this negative. So this negative goes through when you distribute that 2x. So negative 2x times 5x. And you have a negative times a negative here. So you will want to simplify the top. So we do have a 5x squared and a negative 10x squared. 4x and a 5. You may leave the bottom just like this. The only time you would ever want to simplify is if you could potentially factor the top and it does cancel. So if I could factor this top, which I cannot, and it's simplified with the bottom, I would want to do that, but I can't here. There is nothing I can do to simplify it. Sometimes you'll also see like 2x squared plus 4 on the bottom, and then you'll see a 2 for everything in the top. That is a time when you could actually pull something out of it, and then you'd want to simplify that if you can. So if you can pull a single number out and simplify it that way, then you could simplify that with the top. In this case, nothing can simplify, so this is my answer for my derivative here. So this would be my y prime derivative here. All right, so if I were to do this one, I would probably rewrite that top to 3 minus x to the negative 1 over x plus 5. And then my derivative of my top is going to be negative times the negative, so that's the 3 goes away. This becomes a positive x to the negative 2 over, and my, well, we're not going to do over, we'll just do the derivative. So my derivative here of the top is that. My derivative of the bottom is just 1, right? Everybody see that? Then I'm going to plug it in. The derivative of the top times the bottom minus the top times the derivative of the bottom, right? All over the bottom squared. All right, your biggest problem here is going to be figuring out these exponents, right? Do the same process. This is x to the 1 power, right? So x to the negative 2 times x to the 1. So we're going to add it, negative 2 plus 1, right? So x to the negative 1 plus 5x to the negative 2. Distribute a negative, minus 3 plus x to the negative 1. All over x plus 5 squared. There's different ways to do this. I don't know how the book did it, honestly. I just leave it in exponential form instead of fraction form until the end. But that's just my process there. So I combine it all, and then I can get common denominators and all that good stuff.
Do you have to take it out of that form, or can you just leave it in the negative power?
Yeah, you cannot leave it in the negative power. That's not an acceptable answer for sure. You want to combine these guys, right? So I have a 1x to the negative 1 and a 1x to the negative 1. So I have a 2x to the negative 1 plus 5x to the negative 2 minus 3. All over x plus 5 squared. So now I'm going to put it in positive exponential form. So I'm going to rewrite this to 2 over x plus 5 over x squared minus 3. And I'm just going to do 3 over 1 here.
Over x plus 5 squared.
Mm-hmm.
That's so gross. That's the worst thing that's happened to me. Why would you want the derivative of that? Just out of curiosity.
Well, so here's what we can do, honestly. I'm going to show you a secondary way to do this, just because I don't know that everyone would think to do what I'm going to do next. Here's what you can do. You can multiply the top and bottom by your common denominator. All right? So if I were to do that, I could multiply the top, all of it by x squared, and I could multiply the entire bottom by x squared. Right? And it would cancel out, so I would have 2x plus 5 minus 3x squared, right? Does that make sense?
Mhm.
I just multiplied a fraction top and bottom by the same thing. Yes? Does that make sense? And so when I multiply this cancels and I'm left with 1x, that canceled and that. And then on the bottom I have x squared, x plus 5, quantity squared. Right?
So you would want us to do that and take it all the way down?
Yeah, you do want to simplify it. Now, the other thing you can do is you can simplify it at the beginning. So I'm going to show you a secondary way to do this. Most people don't think about canceling that guy out. So I have this as my original. So rewrite it again and do 3 minus 1 over x all over x plus 5. I can get rid of it right here by doing exactly what I did at the end there. I can multiply this by common denominator of x, just like that. Right, so I get 3x minus 1 over x squared plus 5x. And you can do the whole process again, right?
It's probably easy.
Right, yeah. So when you have something like a denominator, think about your rules of simplifying a complex fraction. One of your ways of simplifying a complex fraction, which is what this is, a fraction over a fraction, is to multiply everything by your common denominator, right? And so we've been rewriting to negative exponents, which, I mean, it works. You can see that we were able to accomplish that. But getting rid of it at first sometimes makes it easier, much easier. This is a much easier quotient rule to do by getting rid of that denominator first. Think about when you were, solving equations that had variables and fractions. We multiplied the whole equation by my common denominator to get rid of the denominator. That's the same process here. So when you have something like this, you may want to consider simplifying your complex fraction first and then doing your quotient rule. Make sense? Yes. All right, so let's look at some of the rewriting of these. How do I know when I need to use the quotient rule? Well, when you have a function on top and a function on bottom. If you do not have a function on bottom or a function on top and you just have a number, there's typically a way to rewrite it, okay? So like this guy right here, this first one, this would not require my quotient rule. Why? Well, I could rewrite it with just a 1/6 in front. Everybody see that? Because it was just a 6 on bottom. If you did the quotient rule, when you do the derivative of g of x, it's going to be 0 because it's 6, right? And it's going to zero out. And so you're going to have this long process that's going to zero out part of it. And you've made more work than you really need to for yourself. Same thing here. This does not require the quotient rule. You can rewrite it as 5/8. All right. This one, why would this not require the quotient rule? Well, the negative 3 over 7 can be pulled out, and I can actually cancel an x out of everything before I start, right? And so if you did the quotient rule here, you would actually get to the end and cancel an x out, and your x would disappear anyway. And so just like we did on this last problem, it's much easier to simplify up front. So the first thing you're going to look at is, can I simplify this before I start? Don't just jump right into it and assume that you have to do the whole thing. Same thing with this guy. Does not require the quotient rule. 9/5 x to the negative 2 is going to be much easier than the quotient rule. And so you're going to find that there are times when rewriting is going to make it much easier, simplifying up front. All right, so let's try a couple of these. So these are based off of the quotient rule. Why? Because they're all quotients. Tangent is what? Sine over cosine, right? So we have the sine over the cosine. And if I do the quotient rule, I am going to get the derivative of top cosine, derivative of negative sine, and you're going to end up with your secant of x. We're just going to do one of these, and the rest of them I would just memorize. Like, I'm never going to make you do the proof for it, right? But I want you to show, I'm going to show you how it works. So this guy is tangent. All right, which means the derivative of top is cosine of x. The derivative of the bottom is negative sine of x. So I have the derivative of the top times the bottom minus the top, which is sine of x, times the derivative of the bottom, all over the bottom squared. All right, that's technically cosine of x squared. Okay, so this cosine times cosine, that is cosine squared. Negative negative is plus, sine times sine is sine squared. Cosine squared. What is sine squared plus cosine squared? Always. Pythagorean identity is 1 over cosine squared. What is the reciprocal of cosine? There we go. All right.
I forgot about that.
This is now starting to get difficult.
So, I would memorize these. There is a pattern. Pay attention to the pattern. Tangent is secant squared, cotangent's negative cosecant squared. Those line up, right? So tangent goes to secant squared, cotangent goes to negative cosecant squared. Secant is secant tangent, cosecant is negative cosecant cotangent. You need to memorize these. So you can do, flashcards, I don't care. But if you don't memorize these, you're gonna have to do the quotient rule to figure them out. That's a lot of work when you could just memorize them. So we now have all 6 of our functions. Sine is cosine, cosine is negative sine. Tangent is secant squared, cotangent's negative cosecant squared. Secant is secant tangent, cosecant, negative cosecant cotangent. Okay? And so just memorize them. If not, you're gonna have to do this every time I give you a trig function.
No.
That's a lot of work. Right? A lot of work. Just memorize them.
So,
Okay? This is when you have something like this. I just want to do the derivative. Well, this is not hard now because I know the derivative of x is just 1. I know the derivative of tangent is secant squared. I am done. Boom. That is my derivative, right? This is product rule. All right? Derivative of the first, that's 1 times the second, secant of x. Plus the first, derivative of the second. Well, secant is secant tangent. Secant x tangent x. So my derivative is going to be secant x plus x, secant tangent x.
That's so much
Right.
letters in a math.
But it's also so much easier than going through the quotient rule for secant. Right? Like, I don't want to do that. Especially quotient combined with product rule. What? No, thank you. Like, no.
That just looks like that answer.
In the book, they factor the secant out, but I would not require that because that's no more simple than the first way. The only reason you would do that is the logic is that if you had to use that in something, it's going to be easier to work with like this. Of x is just 1. The derivative of secant is secant tangent. That is the derivative.
oh.
Right. Secant's 1 over cosine. So cosine to the negative 1. So it's actually a chain rule, which we haven't talked about yet. But when we do chain rule, you'll see why you get secant tangent from that. Mm-hmm. So here's the thing. There are multiple ways to differentiate. If I were to see this first one, I could use quotient rule. Or my brain could say, well, I could also rewrite it if I wanted to, right? If I wanted to rewrite this instead of using quotient rule, I could say 1 over sine of x minus cosine of x over sine of x, which is cosecant of x minus cotangent of x. And then I could just differentiate that instead of using the quotient rule. So it really helps to remember like your reciprocal functions and all of that from trig, because you can certainly use the quotient rule if you want to, but you can see how the quotient rule is very drawn out. And anytime you have a longer process, like the limit process of derivatives, you have more room for error. Whereas I have less room for error doing this derivative, the second one, right? Because I remembered, I can just rewrite it. 1 over sine, well, that's cosecant. And I know cosecant's negative cosecant cotangent, right? And so sometimes rewriting these using your trig identities that you obviously have memorized and you know backwards and forwards, it helps you when you're doing this, right? But I mean, truly, the quotient identities, the reciprocal identities, like we know that sine relates to secant and that cosine relates to, you know, I mean, we know that those relate to each other somehow by reciprocals, right? Hopefully. We know that tangent is sine over cosine. Like, so this is stuff that's been ingrained for now 2 years, right? 3rd year talking about this. And so if you don't remember your quotient, you may want to go back and be like, oh, quotient, reciprocal, I know those. Pythagorean identity, that just helped us when we did that because we were able to recognize it.